Shankar, if you can quickly confirm till where have we reached, what we are doing today, and what is it going to be like on next class on Sunday?
Yeah, so last time we looked at Aristotle's physics in the context of discussing how we figured out the shape of the Earth. So today we will look at um, extensions to Aristotle's cosmology, um, focusing on the contributions of Ptolemy and Eratosthenes, two of the um, geographers, astronomers who followed Aristotle. Next time, we will jump forward to Copernicus and Galileo and their contributions to astronomy. And then after that, we will be, uh, we will look at Galileo's mechanics, which is essentially the kinematics that is found in that 11th class physics starts with. So after today's class and next class on Galileo's astronomy, we would be, you know, in the realm of 1D kinematics.
Which would mean
And
1D kinematics would mean we would also start dabbling with calculus at some point of time, right?
yeah, I'll try to cover as much of 1D kinematics as possible without calculus. Specifically, free fall motion is uniformly accelerated, and it's possible to uh, learn it without calculus, but I think calculus will definitely help understand when the motion is not uniformly accelerated, as well as all the later topics that are going to come in mechanics. So yeah, at that point uh, we'll have to get into calculus.
Okay. So, guys, just to be sure, those who are attending, if you have gone through chapter number 2, structure of atom in chemistry, initial part of structure of atom is all kind of hypotheses and postulates which were there to try and understand what is matter composed of. And then there is a substantial description of Niels Bohr theory, and then there is a quantum mechanical model. Uh, if uh, I don't know, Omkar can correct me. The approach that we are taking, we are calling these lectures a new way of learning physics. The idea is to help you understand how we arrived at, for example, if we stop where your book starts in terms of F is equal to ma and some of the ways, some of the equations of motion, etc. We arrived at there, the Newtonian mechanics, after a significant journey. Part of that journey where we have started is Aristotle. We are going to go to Ptolemy, and next class we are going to go to Copernicus and Galileo. But what we are trying to understand is all these people struggled with specific problems, came out with theories and hypotheses. Some got proved right, some got proved wrong, and ultimately we arrived at a place which started making more sense. Some of it is in your textbooks of NCRT, but that is where we are trying to reach. Why we are studying all of this stuff is to start making sense of why are we studying all that stuff which is there in your book. Why do we solve questions? Ultimately, physics is about understanding nature. Mankind has tried to understand nature for a long, long time. Where we are is a culmination of a lot of effort of our forefathers. And once you understand it, the logic would start becoming clear. So, all the people who are attending this class right now, are you able to understand what we just said, and can we move forward? If you can quickly reply in chat, that would be good. And then we start moving forward. And it would start getting connected to your course curriculum from next week onwards, as Omkar said. This class and the class on Sunday on Galileo and Copernicus, and then we start moving forward. Guys, if you can quickly reply, today we are not in the Zoom video format, we are in a webinar format, and you can use chat. Omkar, I assume everyone is going to be mute, and you can unmute them when they want to talk.
Yeah, I think someone just commented that chat is disabled.
Chat is disabled. Okay, that is awesome. How does that happen? Panelists can chat with everyone. Okay, I got it. My bad. Okay, now you can write. Please tell us, are all of you comfortable? Do all of you understand what is the logic? Thank you so much. Very good. So let's start. Sit peacefully. Enjoy this lecture with Dr. Omkar Deshpande. I wish I could have studied with from a person like Omkar when I was at your age, but that's fine. I get to learn it now. Omkar, please go ahead. Over to you.
All right. All right. Welcome back. So, if you have, there's one person who's raised their hand. Should we just take the question in case they have any technical difficulty or
Sure.
Drona? Okay. I don't see, I don't see him now. Anyway, so I'll start. So, welcome back. I am assuming here that you have gone through the recording or you attended the previous session on the shape of the Earth, in the context of which we discussed the old physics of Aristotle, who is known as the philosopher because of his dominant influence in so many subjects in the history of the Western intellectual tradition. So his physics in particular was dominant for over 2000 years, and um, there was really nothing better that people could come up with for a long time. So just to summarize, Aristotle divided all all the things that you see in the material world as fundamentally made up of four elements, right? And those elements were, you can say, solids, liquids, gases, and heat, or earth, water, air, and fire, to use the more traditional terminology. So solids and liquids, earth and water, were known as the heavy elements. Their fundamental property was that if you drop an object that is predominated by the elements earth and water, it would tend to fall down, which means towards the center of the universe. Remember, we changed our orientation of space. When we say falling down, we mean falling towards the center of the universe. Rising up, like air and fire do, means moving away from the center of the universe. And so, natural motion um, in the terrestrial world is linear. It's either towards the center of the universe or away from the center of the universe. Now, the objects that make up the world around us are not purely earth. They're not purely water. Even if you take river water or whatever water, uh, ocean water, rainwater, whatever was available in that time, and if you boil it, people would see that it always left behind some solid residue because there would be some dissolved salts and all in water. But the way they would interpret this is even so-called pure water is not 100% composed of the element water, but it is mixed with a little bit of earth, right? And even a solid rock would not be 100% earth. It might be 95, 96% earth, but it might have a little bit of water, a little bit of air, and a little bit of heat inside. So you never found these elements in their pure form, but always in some combination. But that combination of what percentage of earth, water, air, and fire make up an object could be very different. And that's what would lead to different properties of materials depending on which element dominates to what extent. Moreover, uh, I didn't mention this last time, but if you take two different solid objects, let's say you take a pebble and you take a rock, which are both predominated by the element earth, but a rock has a greater amount of the element earth in it, right, in terms of the absolute amount. So this is heavier right? Both are heavy, both are dominated by the element Earth, but this is heavier. And because it's heavier, if you drop them both at the same time, because the larger rock is heavier, it's going to fall faster, will fall, will fall with a greater speed. And so what you should find is that if this is the ground, an object that has more amount of earth in it should reach the ground faster than an object that has less amount of earth in it. So this is part of Aristotle's, the prediction of Aristotle's physics. Now, I mentioned that Aristotle's physics was actually the main argument uh, that Aristotle used for justifying why the Earth is spherical and at found at the center of the universe. It follows directly from his physics. It's at the center of the universe because the landmass we live on, which is made up primarily of earth and water, even if you were to blast it apart, it would re-aggregate around the center of the universe in a way that all the particles making up the landmass are as close as possible to the center, which means they would arrange themselves in the shape of a sphere. And once they are at the center, there is no further tendency to move. So it doesn't make sense to think of the Earth as rotating, or the landmass we live on as rotating. There's no reason why something made of earth and water would rotate uh, in circular motion. There's no reason why it would revolve around the sun or move around anything else. Okay, so we have a geocentric universe in Aristotle's cosmology, and we have a geostationary universe. Okay, so that this cosmology follows from his physics, and we looked at other examples, other arguments that he gives for why the Earth is spherical, which I'm not going to review again. Um and in addition to these four elements making up the terrestrial world, in the celestial world, where we do see circular motion happening all the time, right? We might cause temporary circular motion on Earth by rolling a ball uh, or by spinning a ball, but it's temporary. Okay, it's an example of unnatural violent motion, as I mentioned last time. Violent motion is always initiated by a, um, a living thing, a soul, and it is temporary. It will come to um an end, after which the motion would be entirely natural. But in the celestial realm, you have the planets, the sun, the moon, the stars that perennially revolve in circles, and that's because they are made of a fifth element called ether, whose natural tendency is to move in circles. So circular motion in the celestial realm, linear motion in the terrestrial realm. This is how natural motion is like in the universe. And I also mentioned that circular motion fits in well with the idea that there are divine entities in the celestial realm, because the Greek gods, for example, did not die, right? Once they were born, they were eternal. And so circular motion indicates something that does not have a beginning or an end. So it's perfect. The shape of a circle is perfect and signifies eternity in that sense. So there was also this spiritual, religious meaning into which this kind of cosmology or physics fit. Now, Aristotle tutored Alexander the Great, as you might remember from your history, and Alexander conquered most of the world that was known to the Greeks, right? all the way up to northwest India. But then, his men were reluctant to go on further. While going back to Greece, Alexander caught a fever and he died in the city of Babylon at a pretty young age. But um, he had also taken over Egypt before he, came east to Persia and then India. Uh, he had he was declared the Pharaoh of Egypt when he went down to Egypt. It was a non-violent takeover. I mean, the Greeks had regard for the Egyptians, and so by taking over the position of um Pharaoh, Alexander essentially became the de facto ruler of Egypt. He set up a city on the northern coast of Egypt called Alexandria, the blueprint of a city. That city was actually completed by um, one of his successors. So when Alexander died, his empire was carved out into different pieces. The piece that was the Egyptian part of his empire got controlled by one of his generals whose name was Ptolemy. And Ptolemy is the one who actually built this city of Alexandria. Ptolemy and his son, who was also called Ptolemy, which is why you have Ptolemy the first, then Ptolemy the second, and a bunch of Ptolemies who are ruling as pharaohs in Egypt. They were actually Greek, but they ruled as pharaohs. And also, some of them were females, so there were multiple Cleopatras also, just like there were multiple Ptolemies. Anyway, so Ptolemy sets up uh, builds this city of Alexandria, and in this city, he builds something like a modern day university. It was called the Museum of Alexandria, one of um, actually the most intellectual um, place to be in the Western world at that time. So I mentioned this, I think, last time that there was a library he established next to the museum, which had pretty much all the texts in the known world from that time, more than 500,000 texts. And scholars from all around the Western world were invited to come and live there and given a stipend, no tax. All they had to do was lecture, do research, talk to one another, and um, develop new ideas. So um, there were a number of ancient scientists and philosophers who emerged out of Alexandria because of that environment that the Ptolemies set up. So, this is actually a painting from the Italian Renaissance, one of the famous painters from that time, Raphael. He he painted uh, 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 this vision of all the Greek philosophers shown together in a single painting. The name of the painting was the School of Athens, and at the very center of the painting, he put the two greatest Greek philosophers, Plato and his student Aristotle, next to each other. And there were other philosophers who are depicted everywhere. There's Pythagoras here. Um, there is Socrates here. This might be Alexander himself. We don't know. Uh, but a lot of the famous philosophers are shown here. Now, if you zoom into this part of the picture, this, by the way, is Euclid. You've studied Euclidean geometry in your ninth or 10th grade, right? So Euclidean geometry was systematic, goes back to a book that Euclid wrote. Uh, and here you see him bent over um, using a compass or something like that, and others are carefully looking at his constructions. But here in this part of the figure, if I were to just zoom in, you actually see the painter Raphael himself. He inserted himself into his own painting, but he is next to this figure whose face you can't see, but you can see he's wearing a crown on his head. This is Ptolemy, uh, the most famous astronomer from the ancient world. You can see him holding a spherical Earth model, and he's shown as wearing a crown because Raphael mistakenly thought that he was related to, the Ptolemies, the pharaohs who ruled Egypt. But the Ptolemy we are talking about was just an astronomer. He was not related to the rulers of Egypt, although he was also um, Greek, like those rulers, but he was not one of them. Now he made numerous observations of the night sky from Alexandria, and he wrote many important books. So if you were to be educated in the Western world uh, for more than 1,400 or 500 years, you would study the geometry of Euclid, which you still do. You don't study Euclid's original work, the elements, but you are essentially studying Euclidean geometry when you study geometry. And for astronomy, you would study Ptolemy's work. So his work on astronomy was so influential that all earlier works disappeared. I mean, nobody really studied them, they were not preserved. And so, unfortunately, just like we don't have earlier texts on geometry before Euclid, we don't have um, earlier texts on astronomy before Ptolemy. So he was considered the supreme authority in the field, unchallenged until Copernicus finally challenged his model. We don't know anything else about his personal life. All that we have from him is his famous work that is known as the Almagest. All right, so this is just you know, the name of the work was not the Almagest. This is more like um, an Arabic name translated into Latin. The original name was Megalis Syntaxis, but Almagest is how it's known today. This is sort of a picture of the Latin edition published in the 1500s. And there is a quote attributed to Ptolemy, I've mentioned that before. For him, astronomy, astrology, um, you know, big questions about existence, they were all part of one and the same subject. So he supposedly said, I know my day's life is marked for death, but when I search into the close revolving spirals of stars, the circular trajectories, my feet are no longer touching the earth. He feels that he is just there by the side of Zeus himself, taking his share of immortality. So, what did Ptolemy add uh, to the relatively simple cosmology that we saw last time? So, remember, last time we saw a simple model of the universe, geocentric, where there was this inner shell made up of the Earth and the atmosphere around it. Um, um, and then there were concentric shells surrounding um, this inner terrestrial world, which had the moon, the sun, the other five planets, and finally the outermost shell was the celestial sphere of stars. So that was the relatively simple geocentric model. Now, because Ptolemy was very interested in predicting the positions of the sun, the moon, the planets, and all for any time in the future, he had to make his model a lot more numerical, right? Very mathematical, so that those predictions could be made. You couldn't just qualitatively say that the planets move in their own spheres. That's not sufficient. He had to come up with what relative speed do they move? What right? With what um, speed do the planets move relative to the background stars? We know that they wander. That's why they're called as planets. So all that was important to nail down. And so I'll give you three examples of how observations that could not be accounted for by the simplistic model we saw were accounted for by Ptolemy in his model, making it very precise, but also very complex. One of the observations that one can make in the night sky um, is not just that planets move relative to the stars, relative to the background stars, but that they show a peculiar kind of motion. Remember last time I talked about how the sun moves relative to the background stars. It always seems to lag behind consistently by 4 minutes or so every day. But it's consistent, right? It's like it's consistently lagging behind by 4 minutes by 1 degree angle. And so after 360 degrees, you would be, back to the same constellation behind the sun. Planets behave in a more or move in a more complicated way relative to the background stars. Normally, for most part of the year, they also will have, they will also uh, lag behind, if you want to call it that. But for some for some days or for some weeks, you might find them behaving in a weird way. So here you have successive snapshots of a planet relative to the background star. So remember that the entire background is moving, rotating once every 24 hours, right? Plus or minus 4 minutes. But uh, the entire background is rotating, and the planet, the sphere that each planet is in, is also rotating. So as a first approximation, think of everything rotating with the same angular speed, if you want to call it that, right? Once roughly around every 24 hours. But then on every successive night, if you were to record the background stars behind a planet, you will see that the background varies and the planet consistently wanders relative to the background stars. But then something weird happens where for a few days or for a few weeks, the planet might appear to turn around and move in the opposite direction relative to the stars. And then again, it resumes its normal forward motion relative to that background. So, this weird turning around is something to be explained by the model. And this is something that could not be explained by the earlier simple models. So, this turning around is called retrograde motion, and it is shown by various planets. Okay, not the sun, but the other planets, like Mars, for example, shows very prominent retrograde motion. And so, how do you explain this? Um, like, does the sphere of Mars suddenly like change its angular speed for some time and then again change it? That would be weird. One of the things that the Greeks like to do is to explain things using simple geometry and uniform circular motion only. Okay, in this they were biased by Plato. Plato was Aristotle's teacher. He was a popularizer of mathematics. He believed that if you want to be a philosopher, you have to study mathematics, specifically geometry. And he said that he gave this task to all his students that you need to explain the cosmos using uniform circular motion, a model that has only uniform circular motion um, in the night sky, right? Because everything there is perfect, made of ether, going in circles at the same speed. So how do you how do you extend this model to without violating uniform circular motion while still being able to explain this kind of observation? Here was, well, this was not Ptolemy's solution, but this was something he incorporated into his model with the right numbers to make it really precise. So imagine here you have Earth, right at the center, and we are just focused on Mars because we want to explain how this happens. What Ptolemy said is if Mars was moving in uniform circular motion around the Earth, then it would appear to lag behind consistently just like the sun does. But it seems to move behind. So in order to account for that, he He gave this model where, and like I said, he didn't come up with this idea, but he incorporated it in a way that was numerically very precise. So here you have Mars that is going in a small circle around a point on a larger orbit. Okay. So Mars goes in a small circle around this point, and this point is going in uniform circular motion around the Earth. Mars is going in uniform circular motion around this point, and this point is moving in uniform circular motion around the Earth. So you actually have a smaller circular motion that is superimposed on a larger circular motion. So why, how does this explain retrograde motion? Well, because for part of the time, you see Mars is actually going behind, right? You can adjust the speed of Mars along the smaller circle. You can adjust the speed of um, this point, which is actually going around the Earth in this larger circle. You can vary those. You have two parameters you can fiddle around with. And if you come up with the right speeds for those two the right numbers for those two speeds, you will see that when Mars is actually going back, and maybe this point is moving forward slower and Mars is going at a faster speed, then overall, when you add up the speed with which it's going behind and the slower speed with which this point is going forward, you might temporarily find Mars going behind, right? Mostly it moves forward, but for smaller periods of time, it appears to move behind just because it's going back um, along this smaller circle. This smaller circle is called an epicycle. You don't need to know the terminology, but there is this standard terminology in astronomy. The larger circle is called the deferent, and uh, so you have these epicycles. Okay, uniform circular motion superimposed on top of a larger uniform circular motion. Mars goes around uh, the center of a small circle, and the center of that smaller circle itself goes in a larger circle around the Earth. This is how retrograde motion of Mars was uh, explained. Okay, so ether is not just going in simple circles, right? You can have circular motion on top of other circular motions in the heavens, and that causes this pattern. In fact, you can also see here that while Mars is going back, whenever you see this, like the overall trajectory would be like this. Whenever you see Mars going back, it's also a little closer to the Earth, right? And this also matched observations that, whenever Mars appeared to show this weird behavior, um, careful measurements showed that that it appeared to be brighter. It appeared to be brighter during that phase, indicating that perhaps it was a little closer to the Earth. And so that is also accounted for in the model because it is a little closer to the Earth when moving backwards. So retro means backwards. Uh, for most of the year, Mars shows prograde motion. Pro means forward, but for part of the year, it shows retrograde motion, and this is how it's explained. All right, so that was one complication in Ptolemy's model. Here's another complication. Again, the complication is because of the need to explain an observation that could not be accounted for by the earlier model. It is known that the sun also appears to be a little larger in winter time. Let's say at the same time when it's noon, right? When the sun directly goes over the meridian line, as we saw in an earlier session. It appears to be a little larger in the winter than in the summer. So how do we explain that? Now the sun does not have that epicyclic motion. There's no retrograde motion for the sun. So why is it that the sun appears to be a little closer? A little bigger in the winter? Well, to account for that, here's what Ptolemy did. This is the center of the universe, okay, which is also coinciding with the center of all the spherical shells, including the shell of the sun. He took the Earth and he moved it a little off center, a little bit off center, so that um, now this is here you see Mars or one of the planets undergoing that epicyclic motion as the center of that epicycle moves around the Earth. But just imagine we are looking at the sun now, right? There's no epicyclic motion. The sun appears to consistently move um, around the celestial sphere. The important thing to keep in mind whenever thinking of these circular motion models is everything has to be analyzed relative to the background celestial sphere. Okay, because we know everything is rotating around once every 24 hours. It's that difference relative to the background celestial sphere which is what matters. So we know that in winter time, the sun will be in front of some specific constellations uh, which lie on that background celestial sphere. Now, whenever it's in front of those constellations, it appears to be a little bigger. So maybe put the Earth a little off center towards those constellations in the direction of, those uh, those constellations, so that whenever um, the sun appears to be in front of them, it would appear to be a little larger because this is the direction in which the sun would be in winter time in front of those constellations. Does that make sense? That uh, you put the Earth a little off center. This actually, as you can immediately see, is not a very satisfying solution, because now what are we saying? We are saying that the center of the universe is this. The Earth is not exact, it's almost at the center of the universe, but not exactly at the center of the universe. So, in a sense, strictly speaking, this violates Aristotle's physics. But, because this was almost at the center, so people thought, okay, this is a decent approximation. So things do tend to fall um, towards the center, but with some margin of error. Not a very satisfying solution. This is actually one of the reasons why Copernicus is going to be very dissatisfied with uh, Ptolemy's model. That he felt that it was sort of there's some lack of consistency between um, you know the circular motions, complicated circular motions here, and the physics of Aristotle. And so he thought that there needs to be something simpler to explain the motions rather than something dissatisfying like this. So, so this is how that other observation was explained. Why is the sun a little bigger in winter time? Yet another observation was that if you imagine the sun lagging behind the celestial sphere, going 360 degrees in 1 year. Well, if you measure how many days it takes for the sun to move 180 degrees, that should be exactly 180 days, right? Or almost 180 days. 365 is the exact number, so maybe 182 days or something like that. It should take to move from, let's say, um, uh, uh, well, we haven't talked about the equinoxes and the solstices, so I'm hesitant to use that terminology. But um okay, let me just explain it qualitatively that um, during winter, right? Imagine dividing the year into two halves. Let's say from June 21st to roughly December 21st, or um, actually, let's divide it from September to March. Okay, September to March, and then from March to September, right? So let's say September 21st to March 21st, and then March 21st to September 21st. Those points supposedly mark the beginning of the fall season and the beginning of the spring season. Anyway, the sun appears to move a little faster um, during winter in front of the celestial sphere than in the summer. So if you measure how long it takes to cover 180 degrees, during winter time, it's actually 6 days less than in the summer. So it takes 6 days longer to move one half of the celestial sphere than the other half. So that's also weird. I mean, careful observations show this. So then why, like, how do you explain this? And then, so for this, in Ptolemy's model, what he did is he said, you know what? The sun is actually undergoing uniform circular motion, right? It's not like the angular speed is varying, but it's maintaining the same angular speed, not with respect to the center of the universe or with respect to the Earth, which is now off center, but with respect to another point, which is also off center. So as the sun goes around in a circle, so think of the angle it makes. So let's say in one day, it covers this angle. Then in the next day, it's going to cover this angle. Then in the next day, it's going to cover this angle. And all of these angles are the same. Okay. So for the angular speed to be same around a point which is not exactly at the center, the linear speed will have to change. It will have to actually go faster. Sorry, yeah, faster here to maintain the same angle, and slower, or actually it's the other way. It'll have to go. Okay, I'm not cutting this into 360 or 365 days exactly, but imagine that it has to make the same angle, it has to traverse the same angle relative to this point, not relative to the center. If it was relative to the center, then you would have exactly uniform circular motion, same angular speed every day, same linear speed every day. Um, but if it has to make an angular velocity that is constant every day with respect to a point that is off center, then, for the same angle here, uh, to make the same angle here, it would actually need to, um, go faster in some part of the year and slower in the other part. Okay, and that is how he explained it. So now it's not going at constant linear speed around the circle. It's actually going at constant angular speed, and that too not around the center. So it's more complicated, right? It's looking uh, more complicated, and so but if you introduce these complications, you come up with perfect predictions. Okay, so all of these extra complications were not invented by Ptolemy, but he incorporated them with the right numbers, with the right parameters, in a way that his model made the best possible predictions for where the planets would be at any point in the future compared to any other competing alternative, which is why his model was dominant. It's still used in planetarium softwares today. So let me see if I can show you how there used to be a flash animation of this, which unfortunately is no longer usable because Adobe has eliminated that. It's okay, I'm just sharing my screen here. Let me know if you can see you can go to this YouTube video independently as well. But I'm just going to play this. Kapil, let me know if you can see this.
I can see it, Omkar. I think students would also be.
Okay,
I'm so happy this thing is being taught to students.
sure. So if you look here, you have the Earth-centered universe. The Earth is probably very small, slightly off-center. I don't know how much the creator of this animation was faithful to Ptolemy's model, but it's very tiny. But you can see some of the planets outside, right? Jupiter and Saturn probably here, that are moving more slowly. But you can see the retrograde motion, right, for all the planets here. Uh, You can see Mars here, probably because it's shown in red. The sun is moving in a perfect circle, no epicycles. But I just want you to get a sense of how complicated it is. And notice that all this is relative to the background stars. Now imagine the entire background is rotating once every 24 hours also around the Earth. So all this motion that you see happening here is relative to the background stars. So you have to add the motion of the background itself to get the absolute motion, which is what we see with our naked eyes. Okay, so you can see Mars moving in an epicycle. They've shown this faint epicycle. You have this epicycle for Jupiter. And you know what? Even what I have explained so far is not the most complex version of the model, because what you had were not just epicycles, but epicycles on top of epicycles. So if you want to be exactly precise, I'm just going to stop sharing this and uh, go back to. I'm going to come to questions just after this, but just want to complete my point here that even the epicycle diagram that I showed you a few minutes ago is not the most complex version of the model which would make precise predictions. If you want to be even more precise, then you would actually put a planet on a smaller epicycle whose center is moving along around a larger epicycle whose center is moving around the Earth. Right? So uh, because even small deviations from the predictions were to be taken seriously. And so how would you incorporate them? Well, you add one more parameter by adding one more epicycle. That gives you more freedom to play around with three numbers now instead of two numbers and make the observations fit uh, that model. So that was, in essence, Ptolemy's model. Obviously, people would spend their whole life perfecting this model and making predictions based on it. And in that context, astrology was also important. So Ptolemy's model was very important for astrologers. Um, so yeah, any questions on this? No questions. Did I stop sharing, Kapil? Or can you see my slide?
Now you're sharing.
Okay.
Yeah, now the screen is visible. Mathematical principles Ptolemy uses in the
Okay.
Almagest.
Sure. Yeah. Uh, yeah. So yeah, and like I said, with respect to this point, to make equal angles, you would actually have to move um, slower during this part of the year when the planet is moving here, and faster here to make the same angle as you were making when you were closer to that point on the other side. So um, faster here means with respect to the Earth, you would be actually moving faster. Those of you who studied Kepler's laws, you know that this is what the data was pointing to. It's just that Kepler came up with a totally different explanation for it. But uh, anyway, don't want to go. Let's not think about Kepler right now, but just think about how we extended Aristotle's model to make it more precise, although less aesthetically satisfying, because now we don't have the Earth exactly at the center. This uniform circular motion is not really happening at the same speed. It's happening with respect to a point that is not coinciding with the Earth and also not coinciding with the center of the universe. But it's happening at the same angular speed, not the same linear speed. And so it's sort of starting to look a little messy and inelegant. But because it was so precise, the predictions were so accurate, people went with this. Okay, so if there are no questions, then I will just take a few more minutes. I want to come to the second part of today's session. I mentioned I'll talk about Ptolemy and also about Eratosthenes. Someone said I didn't get that epicycle over epicycle part. Well, the idea is just that even with this epicycle model, there were deviations, right, from the predictions, small deviations. So what um, what they did was to add a second epicycle. This is called a double epicycle model. What was shown originally was a single epicycle model. So now in a double epicycle model, you have a planet, which I'm showing in blue now. It's going in this small circle around a point that is moving in a larger circle. Again, you're doing uniform circular motion around a point which is actually moving around the Earth. Okay, so this is called a double epicycle model. And it's kind of like, for those of you who know math, um, if you are given a bunch of points in the Cartesian plane and you're given the freedom to construct, to fit all those points using a polynomial, and let's say you can't fit it, you can always increase the degree of your polynomial to make the curve bend and twist more flexibly to finally fit all those points. So if you are given the freedom to uh, fit any set of data points using an infinite degree polynomial, you'd be able to probably do it, right? Just because you get more parameters when you add, um, if you go from a cubic polynomial to a quartic polynomial, you get an extra parameter to fiddle with. And so that's kind of what's happening here. By adding a second epicycle, you get more freedom to play around with three numbers instead of two numbers so that it fits exactly your observations. But here's the question. Is it more important to exactly fit the observations, or is it more important to explain what's going on? Right? The physics of Aristotle was trying to explain how, the dynamics, how do things actually move. Whereas here we are just trying to fit the kinematics by adding more and more parameters, but the deviation from the dynamics is increasing, right? The deviation from what actually should happen, things should move towards the center of the universe, or things should fall towards the center of the universe. But actually, ether should not fall. We know ether goes in circular motion. And so they probably felt that, well, it's okay. It's okay for ether to go around something that's not exactly the Earth or exactly the center of the universe, right? But then it still gives rise to that question that on the Earth, the elements earth, water, fire, and air, they seem to be rising and falling towards the center of the Earth, not really the center of the universe, if the Earth is not exactly at the center of the universe. So there is that complication. I hope it's clearer now. Um, what exactly is this double epicycle? Okay. So hopefully you see how complicated this model is. Now, the second part, we talked last time about the shape of the Earth. Once the Greeks figured out, using these arguments and observations, that the Earth is spherical, it was natural to ask, how big is this sphere? What's the radius of the Earth? Is that something one can figure out without traveling all around the Earth? So a number of these astronomers and mathematicians who were mostly geometers, because math was essentially geometry and number theory that time. A lot of these people studied at Plato's school when they were young. So Plato, the Greek philosopher Plato, who was Socrates' student, Aristotle's teacher, set up a school called the Academy just outside of Athens. And apparently, outside the school, there was a board, a sign set up, which said, "Let no one who cannot think geometrically enter." It's like the modern equivalent of saying, "Let nobody who does not know math or want to study math enter here." And, if you imagine a school of physics set up by a philosopher like Plato, that's what it would be like. Okay, so Plato he wanted to popularize mathematics, geometry in particular, and one of the students who studied there, so his academy continued for several hundred years after he died. Um, and one of the students who studied there was Eratosthenes. He was actually a Greek who was born in a Greek colony in modern day Libya called Cyrene. But in his early years, he must, he might have traveled to Athens and lived there for his studies. And then, as an adult, he moved to Alexandria. The third Ptolemy, right, the third generation uh, pharaoh Ptolemy, invited him to serve as a tutor for his son in Alexandria, and so he moved there. And remember the Museum of Alexandria, which is like a modern day university. Uh, the president of that university, the title of the president of that university was chief librarian, okay, because the library next to the museum was like the most valuable asset for. In fact, what they would do is any ship that would come into the harbor would be inspected, not for drugs or um, smuggled products, but for books. They would search the ship to see if there were any books in it that were not in the library of Alexandria. And if they were, they would confiscate those books. Not literally steal them, but they would confiscate and they would make a copy and then give you a copy of the book. They would keep the original um, in the museum. So that's how greedy the Ptolemies were about
Well,
making sure that. Sorry?
this is very cool.
Yeah,
I
so
hope the world was like this.
sorry.
I hope the world was like this. People are going crazy about gold and drugs and all the stupid things. The thing to go crazy about are the books. Yeah,
Yeah,
very
and
cool.
you see the result, right? So much of
Yes,
innovation happened as a result
extraordinary.
out of
Extraordinary.
Alexandria. So Ptolemy lived there and he was an astronomer. Now we are talking about a guy who invented the field of geography. Okay, and this was Eratosthenes, who held that position of the president of the university, if you want to call it that. Museum, the word museum meant a temple to the muses. The muses were the Greek goddesses of learning, like you have Saraswati in Hindu culture. You had the muses. There were seven or nine goddesses collectively known as the muses. And so the museum was originally meant as a temple to these Greek goddesses of learning. Today, of course, we preserve artifacts and ancient scrolls or and other things in museums. But originally, the word museum meant that. So Eratosthenes was actually a very versatile scholar, again, interdisciplinary. Okay, his interests were not confined to one narrow area. Uh, he was interested in lots of different things: geography, philosophy, history, astronomy, mathematics, poetry. You will be interested in a lot of things if your curiosity is about the big questions and you follow the big questions. Different big questions will lead you in different directions towards different fields of knowledge. And so you found many such polymaths there. In fact, he was uh, nicknamed Pentathis. Pentathis was actually a name for an athlete in the Greek Olympic Games who would be a champion in multiple different events, right? So Eratosthenes was a champion in different academic areas of knowledge, because of which he was known as Pentathis, although there is a legend that he was also known as Beta, not Alpha, because he was well versed in many different fields, but not the foremost expert in any of them. Kind of like a jack of all trades. We don't know if his he had enemies who called him Beta, but uh, it's possible that he could have, there were lecture halls in the museum which were marked with letters like alpha, beta, and so on, and the classroom that had the letter beta belonged to him. So we don't know this, but uh, it's interesting to think about. Anyway, so coming to one of his key contributions, uh, about which we know today, he calculated the actual size of the Earth. He was not the first person to estimate the size of the Earth, nor the last, but his estimate was extremely accurate, just 1 to 2%, um, you know, uh, different from what we today know to be the actual size of the Earth. So how did he do it? Again, going back to this, I showed you this quote because what he essentially used was what we would today call as high school geometry, your ninth, 10th grade geometry. That was sufficient to calculate the size of the Earth, and I'll show you how. Now, he started out with the assumption that the Earth is a sphere, and now we know exactly why people thought that it's a sphere. So let's think of a spherical Earth, and that red dot is the center of the Earth. A second assumption that he started with is that the sun is quite far off. Okay, so it's so far away that the rays of light that come from the sun are can be thought of as parallel. Right? If the sun was close to the earth, then the rays would not be parallel, they would diverge from the sun. But if you take that divergence point far away, you can approximate the rays of the sun to be parallel to each other. And so here's our visualization right now. We have parallel rays from the sun coming and hitting the earth. Now, uh, in Egypt, the southernmost city was a city called Syene, again on the banks of the Nile. Today, I think it's called Aswan. And um, living in Alexandria, Eratosthenes must have traveled to Syene. And so this is Alexandria on the northern coast of Egypt. Okay, Syene is like the southern end, and Alexandria is at the northern end. Here are their locations on the map. It was thought in his time that the Nile River flowed north to south, so Syene was located directly south of Alexandria on the same meridian. It's a reasonable assumption, approximate, not exactly correct, but he thought they are located along the north-south line. Um, and distances had also been measured. So how would people measure distances? They would get a bunch of people called surveyors who were trained to walk with equal steps and to count the number of steps as they walked from one city to another. And so they walked all the way from Alexandria down south to Syene and measured the length between those two cities to be 5,000 stadia. So stadia was a unit of length used in those times for the length of an Olympic stadium. So that was one unit. So 5,000 stadia, right, back to back stadia would be the length between Alexandria and Syene. So the distances between these two cities were also known. Now, there was a deep well that existed in the town of Syene. And okay, one stadia, this is, I think the stadium at Olympia, where the site of the original Olympic Games. Uh, Approximately 600 feet is what we think one stadium was equal to, but because the very definition of feet was not uniform, so we're not exactly sure. So Syene was a city um, north of the equator, right? It's north of the equator. And there was a well, a deep well that had been dug there. So I'm exaggerating the depth of that well, but notice that if you were to dig a well deep into the earth, you would actually be moving, you'll be digging in a direction that points towards the center of the earth. Okay, so we are looking at it this way. Now, observations again of not night sky, but even the daytime sky showed that there was a special day in the year when the rays of the sun were directly overhead. At noontime, the sun was directly overhead in the town of Syene on that particular day. Okay, so if the sun is directly overhead, its rays would be, and how did they figure it out? Well, because at that moment there would be no shadow cast by the, if you looked deep inside this well, you would not see any shadow cast by the sun. Absolutely no shadows. You would see the sun's image directly in the water uh, inside the well. Okay, because if the sun was at an angle, then there would be a shadow cast by the walls of the well on the opposite side of the well. So this was something that was known through empirical observations. And on that same day, on that same special day, which happens to be the summer solstice. So it turns out that Syene lies on the Tropic of Cancer. And so if in India, I think if you went to Ujjain or some town like that, you would see the same thing happening on the day of the summer solstice. We haven't talked about solstices and equinoxes and all, but uh, uh, just take it as an empirical observation for now that on this location, you had the sun's rays falling vertically. And you could even test that by planting a vertical stick on the ground at Syene. A vertical stick was known as a gnomon. And a gnomon was a very simple object that was used to create sundials in those days because you would look at the tip of the shadow of the gnomon cast by the sun and you would observe how does that tip move during the day. It would move along a trajectory and then the next day that trajectory would be slightly different. Then on the next day that trajectory would be slightly different. And so if you imagine creating 365 trajectories, those trajectories would repeat a year later. And so looking at which particular trajectory the sun was following, you could actually identify which day of the year it is. But anyway, so a gnomon would cast no shadow at noontime um, in the town of Syene. But on that same day, if you placed a gnomon in Alexandria, it would cast a well-defined shadow. So here's how I'm again exaggerating the diagram here. I'm imagining that in the city of Alexandria, there is a vertical stick that has been planted. Um, and the parallel rays of the sun are such that, they are, in the town of Syene, they are falling exactly into the well. So exactly going towards the center of the earth. But in Alexandria, they are off center, right? Because Alexandria is further north and so the earth's surface is curved. But if you were to plant a vertical stick in Alexandria, the direction of that stick would point towards the center of the earth, but the direction of the sun's rays would be different there. And there would be a well-defined shadow that would be cast. So this small stretch that I'm showing here would be the length of the shadow because the tip of the gnomon, um, the sun's rays that hit the tip of the gnomon or that just pass over the tip of the gnomon would hit the land here. So you would get essentially a right angle triangle here And you could measure what this angle is. We mark that. You could measure what this particular blue angle is. So let's say you know what that angle is. Okay. Uh, in fact, there was a very simple device that was used to measure angles. So imagine a hemispherical bowl. Um, Actually, forget it, because that will take a few minutes. I don't want to like unnecessarily deviate. But let's say you know how to measure angles. Okay, you have some kind of protractor, right? The hemispherical bowl or whatever I was about to show you. It's kind of like what a protractor does today. So you measure this angle. That angle was known to be 7.2 degrees or something, but it's not important. But here's how Eratosthenes used high school geometry. I hope you see a Z shape here, right? These are parallel rays of the sun, and there is a symmetrical Z that's formed. From your high school geometry, you might remember that whenever you have a symmetrical Z like this, these two angles, which are known as alternate angles, are always equal, right? So you have two parallel lines making up the extremes of the Z, and then you have a transversal, and so these angles inside a Z are equal. You see a Z here. This angle must be the same as this angle. So I'll make this blue as well. So the shadow cast by a gnomon, the angle made by a gnomon shadow in Alexandria, must be exactly the angle that's formed at the center of the earth by the radius line joining Alexandria to the center and Syene to the center. Now, if I know the distance from Alexandria to Syene, this is 5,000 stadia. 5,000 stadia, this arc length of 5,000 stadia corresponds to a turn or an angle of whatever it was he measured. He measured, I think, 7.2 degrees, yeah, 7 degrees 12 minutes. Okay, so you might remember from an earlier session, 7 degrees 12 minutes would be 7 plus 12 by 60 degrees. That's 7 plus 1/5, 7.2 degrees. So 7.2 degrees, um, a turn of 7.2 degrees makes a distance of 5,000 stadia on the surface of the earth. And so the question is, if we did a full turn of 360 degrees, how much would be the arc length? That would be the circumference of the earth. So uh, actually, if you think about it, 7.2 degrees is what fraction of 360? So 7.2 divided by 360 is 72 divided by 3,600. So this is actually a multiple of 36. 36 times 2 is 72. 36 times 100 is 3,600. So that's 1/50th. 1/50th of the circumference of the earth. So that means the distance from um, Alexandria to Syene is 1/50th of the circumference of the earth, because the angle made at the center is 1/50th of 360 degrees. So if I take this distance and I multiply it by 50, I would get the circumference of the earth, based on which I could get the radius or diameter by dividing by pi. So, or 2 pi. So because the earth is spherical, the ratio formed by the angle at the center to 360, which is 1/50th, is equal to the ratio formed by the distance, the arc length from Alexandria to Syene, and the entire circumference of the earth. So this is the arc length. This 1/50th should be equal to the arc length divided by the circumference. The arc length is known. the circumference is unknown, and so you can get it by uh, multiplying 5,000 stadia by 50, and you would get 250,000 stadia. So there are some correction factors that he had, but if you actually take the you map these units to modern values, you get something that has an error of only 1 or 2% from the actual value. There were some sources of error. Like I said, sine is not exactly on the same north-south meridian as Alexandria. Um, it's also not exactly on the Tropic of Cancer. Um, and the distance was obviously approximate because you had these men who were walking, uh, uh, and that's how they measured lengths in those days, marching from one city to another. So there'll obviously be some error there. But the important thing is the method that Eratosthenes used was remarkably, um, I would say, very insightful, but at the same time, the geometry itself is something you've studied this in your ninth or 10th grade geometry, so it's not hard to understand. But this is how he computed the size of the Earth. Okay, so now this calculation is part of the field of geography. I mentioned that he's considered the father of geography. Geography means what? Geo is the earth. Graphica means to write about, right? To write about the earth or to draw, uh, say, a map of the earth. We don't have his original work on geography, but his arguments for a spherical earth, were part of that. He also drew a map of the world, which was the most accurate in that time. It was actually the first map that used a grid of latitudes and longitudes. Longitudes is just these meridian lines. And you can talk about latitudes on a spherical Earth. These would be the east-west lines that actually go and form small circles or circles around the spherical Earth. So he had latitudes and longitude lines for more than 8,000 uh, places on the Earth and estimates of distances between the locations. So here's like his map. I actually showed you this map last time. Remember when we were talking about elephants existing in this extreme and on that extreme? So notice that this entire landmass of the Earth was placed in the northern hemisphere. Right? The equator was south of everything, and so now we know that Africa actually goes south of the equator. But in his time, he thought there's really no land south of the equator. He also suggested, based on the spherical shape of the Earth and the distances that he calculated on this map, that it's theoretically possible to go around the Earth. If it were not for the vast extent of the Atlantic Sea, one might sail from Spain to India along the same latitude. Parallel means so the latitude lines were known as parallels that time. So you could just stay along the same latitude and go uh, around the Earth. In old age, he became blind, and being a scholar, not being able to read books or parchments, he lost the will to live, and he basically starved himself to death. So that was Eratosthenes. Again, we don't know much about his life, but maybe a little more than Ptolemy. But together, Eratosthenes and Ptolemy, who followed Aristotle, who were masters of the field of geography and astronomy, came up with a model of the Earth and the universe that was more rich in details than what we had from Aristotle's time. And this was kind of the model that was prevalent in Copernicus's time or Columbus's time. Uh, and so we are going to move in the next class to, uh, jump ahead by 1,400 years and see how people started challenging not Eratosthenes' model. Of course, the geography was also made more accurate as people actually started circumnavigating the world. They drew more and more accurate maps. The North American the American landmass was also discovered by Columbus, and so that would change. But more importantly for us, since we are trying to study physics, um, how did Ptolemy's model get challenged? How did Aristotle's physics get challenged? Remember that the physics and the astronomy go together. Ptolemy was implicitly assuming Aristotle's physics in his model, although we saw that there was some tension, right? Some deviation from Aristotle's physics in the way he moved things off center, slightly off center, and in the way he said that uniform circular motion is not really motion at the same speed, but at the same angular velocity. Again, around a point that's not exactly at the center, but it seemed to make the best predictions, and so people went with that model.
Omkar, I have a question.
Yeah.
All this physics in the earlier times, was it only related to astronomy, or like in modern times, they were also applying it into, for example, machines or some other stuff?
So generally, engineering in that time was empirical, like the Romans constructed these bridges and all without really understanding physics, but through trial and error. But there were some exceptions, like Archimedes was a prominent
Yeah.
exception. He created supposedly these war machines, like mastering the mechanisms of levers and pulleys and so on. Uh, Again, not really founded on Newton's laws, but through his own empirical mathematical laws of the lever and pulley and so on, he used the math to in the construction of these war machines, which actually help his city of Syracuse fend off the attack from the Romans for a long time until they finally got inside the city, and unfortunately he was killed uh, in that episode.
Yeah. All right. Guys, any questions? Please feel free to ask. As you can see, the class is still not making you study something without knowing why we are studying it. It is still a lot of fun. So I would strongly recommend, if you have any questions, if something is making you curious, you're not able to figure out what, please feel free to ask.
All right, seems like there are no. Okay, Arohi. Yeah, go ahead, Arohi. You can unmute yourself and ask the question. You're not audible in case you're trying to speak something. You'll have to first unmute yourself.
Have I muted everyone? Aroi, you're not able to speak?
So I've
Hmm.
clicked the ask to unmute button. Uh, so they should be able to unmute themselves, but okay,
I'm
she's
a,
unable to.
let me see if I can help. Hmm. Aroi, try now. Hmm. Why this might be happening? Hmm. I don't know. So Aroi, why don't you ask the question in the chat? And at some point of time, gunpowder also comes into the picture, or that is very late, Omkar?
Uh, that may not be relevant here, right? And you're talking about the colonization of uh,
I think it's,
Asia,
gunpowder.
Africa, and the Americas using
It
guns.
it probably gunpowder probably came out of Greece. No, I'm wrong.
China,
Uh, so that means it is not going to be reasonably early. Okay.
yeah.
My
Well,
bad.
I think 1400 or something is what I roughly remember, but I need to check. Uh, but yeah, I mean, it wasn't, to my knowledge, it wasn't being used as for in wars there, but in Europe they sort of mastered the art of using it in uh,
Yeah, it's one of the four
battles.
inventions of China,
Mm.
AD 904.
Yeah, the Chinese had it early, but the Europeans got it from them. I think 904 is when they got it. It should be
So
later, I think.
904, it was first used for warfare around 904. That's what it says.
Oh,
Guys,
okay.
questions. If you do not have any questions, then we say goodbye to each other and we meet on Sunday morning at 10 a.m. And we are reaching reasonably close to applying the knowledge and the interest that we have developed into our day-to-day physics problem that you will find in books. Good. Thank you, Omkar, and we'll catch up on Sunday.
Okay. Thanks.
Bye.
Thank you all. Bye.